functional theory that deal with uncompensated spin systems where you've got more ups and downs and they're not all paired together in separate orbitals. We'll just put that aside for now. We've got to start somewhere. And there's a wide range of problems actually you can just deal with in this kind of a fashion. So that's going to be our representation. So we're going to have some three-dimensional functions, one for each electron. So now my water molecule is really easy. Right? I mean, like I said, the total data set size for a three-dimensional representation, might be I don't know, maybe 10 kilo pieces of information, 10,000, 50,000 pieces of information times maybe 100 electrons here, 5 megabytes or something. I mean, it's nothing nowadays. So that gives us a very computationally tractable representation. All right, now, the neat thing, this is a theorem, it's the Cohen-Sham theorem. And this I'm not going to prove. Right? I'm just going to have to take this on faith, and I have to refer you to to last year's course. But I do have some of the reading assignments and so forth from last year's course available on the current course website, so you can read about the theorem. But what it tells you is something that you almost might intuitively write down in the first place. In fact, people had something very close to density functional theory called X-alpha theory years before Cohen had proved his Cohen-Sham theorem. And it looks very much like this theorem that I'm about to write down. In fact, what he likes to say is that he made an honest woman out of X-alpha theory. Basically, is what the Cohen-Sham theorem does. What the Cohen-Sham theorem says is that we can actually get the exact same result we would have gotten from this many-body calculation. So we can get the exact ground state energy, which is what we're looking for in the Born-Oppenheimer approximation, and also the exact electron density, which I'll call N of R, which is a number density, number of electrons per unit volume, if we do the following. The first thing is that we can construct that density in the usual way we would expect from having different electrons flying around independently in some quantum states. If I had just one electron, the average density is just the probability of finding the electron somewhere. So if I had just one electron, it would just be the modulus squared of its orbital. But now I've got a whole series of these orbitals, so I had better sum up their individual contributions. And of course, I've got different numbers of electrons in each orbital. So that will give me the density. So I can get those, provided I construct the density this way, and then I follow the following procedure. I'm going to calculate this energy by minimizing them over all possible collections of these wave functions and occupancies, such that certain constraints are obeyed, certain straightforward constraints, in particular that the sum of these occupancies had better add up to the number of electrons in my problem, of course, and also that these orbitals form your standard sort of nice orthonormal set. And that's basically how the theory builds in the Pauli exclusion principle and maintains a proper normalization for the final total density. But again, very commonsensical thing. You might even just think to write this down. And then what we have to minimize then is the total energy of the system written out in a special way. But a way which actually, again, makes fairly intuitive sense. So before I write down the separate terms, let's just review what various pieces I'm going to be expecting. If I look at the energy of the system, energy always comes just in two forms, right? We've got kinetic energy and potential energy. So I've got the kinetic energy of the nuclei. But as we've said, in this Born-Oppenheimer picture, we start by imagining the nuclei is just held fixed in space. So for now, you can just say that that's 0. There's definitely going to be some kind of kinetic energy for the electrons of the system. And that's all we've got, two components, so two kinds of kinetic energy. And now we have all the various forms of interaction that are possible between them. There is the potential energy of the nuclei interacting with the nuclei. course, these nuclei are held at fixed positions in space for now. So they, therefore, their total interaction energy is something we'll write down in a moment, but it's a constant. So that doesn't really affect the minimization very much, does it? Because the minimum of some function plus a constant is just the constant plus the function of the minimum of the function. You can pull that out. And then there are, of course, the other types of interaction. We have the electrons interacting with the nuclei, and the electrons, of course, interacting with the electrons. And that's it, because we just have one type of interaction. Now let's write down these terms in the correct way. So the kinetic energy we would associate with the electrons is pretty much what you would do from your first semester quantum mechanics class, right? Each orbital has a certain expectation for its kinetic energy, which can be written out in the standard operator form. There's minus 1/2 h bar squared, mass of the electron, del squared, acting on the orbital. And that's how much kinetic energy that orbital has. And I've got Fi electrons in that orbital. And I would just sum those up like that. Pretty straightforward. The nuclear term, again, maybe after a good intermediate or even introductory course in electricity and magnetism, we can write these things down. The nuclear interaction, we have to sum up the Coulomb interaction. We've got the famous factor of 1/2 to avoid double counting. We then are summing up over all pairs of nuclei. The ith nucleus would have a positive charge of the atomic number of the corresponding nucleus times the electron times the charge on the other nucleus divided by their distance. And I think I forgot Coulomb's constant. Put that guy in there. And then I can simplify this and rearrange things a little bit. That's 1/2 Coulomb's constant E squared, sum I not j, Zi Zj over Ri minus Rj. Good? Straightforward enough. The electron nuclear interaction, again, it's just the Coulomb interaction. And because now we have direct access to the average number of electrons at any given point in space, this is relatively easy to write down. I just go to every point in space. I look at how many electrons are at that point by taking the density times the volume element. And I multiply by the potential that the nuclei set up at that particular point. And the potential due to the nuclei is, again, just a Coulomb sum. I've got a sum over all the nuclei. I've got, don't forget Coulomb's constant, I always have that problem. Coulomb's constant. I've got, the electron has a charge of minus E. It's interacting with the nucleus of plus charge Zi E. And the distance between them is the location R, where I'm asking for the potential, minus the position of the nucleus. And I can simplify this. And what I like about it is notice the same combination of constants is showing up. KCE squared, sum on I, Zi, R minus R. Good. Any questions so far? And a lot of this stuff, a lot of you guys know. It's important for us to write it down, though, in particular, just to get a consistent notation going. So that's my nuclear potential. And then finally, I have the electron-electron part. This is where we have to be a little bit careful. First, it has a mean field contribution, which would just be the electron density on average interacting with itself. And that's called the Hartree energy, which I'll write down momentarily. And then, actually I'll write it down right now. I want to make a point about it. It's going to be the same kind of term. We have to avoid the double counting. We have to integrate a double integral now to go over all regions in space, right? Usual electrostatic term. The charge density at a given point is minus the electronic charge times the number of electrons there, minus E n of r prime over r minus r prime, like that. And that fits my favorite motif, right? I've got 1/2, same combination of constants, k e e squared, integral, and if you'll allow me to abbreviate things a little bit, integral prime, n at r prime over r minus r prime. I just want to write the dq bars, drive me crazy. That's the Hartree, right? That's just the mean field interaction I'd expect from some cloud of electrons of a given density. The problem with that picture, of course, is that there are correlations among the electrons. When, an electron is sitting, say, at this point in this electron cloud, he does not see the average charge density around him. Because he's there and there's some correlation, the other electrons, of course, try to avoid that spot. First, by Pauli exclusion, and second, because electrons repel each other. So he's going to instantaneously see, if he's sitting at this point R, a different distribution of electrons where something's been hollowed out around him. So there's just something missing from that mean field description. And the real power of the Kohn-Sham theorem is it states that you can write that down in a particularly simple form, and all it depends upon is called the exchange and correlation energy. Exchange referring to the Pauli exclusion effect I had just described, and correlation referring just to the fact that there's additional dynamical correlations that the electrons repel each other. And that can always be written down just in terms of this density constructed from this kind of single particle picture. And somehow, almost by magic, and that's what the last semester was, or last year was about, by finding the right function of this form and carrying out this minimization, even though I'm only thinking about these much more simple single particle orbitals, I can be guaranteed to get the exact ground state energy by this procedure, and correspondingly the exact single particle, the exact average electron density. Even though it's written in terms of single particle orbitals, it'll be exactly the same density that I would get from this full many-body wave function. That's kind of the powerful content of that theorem. I think overall, if you stand back, it seems pretty plausible, right? We've just written down, all the various terms that we would expect, and we're minimizing the energy over all valid orthonormal sets of wave functions, and minimizing over the fillings so that we get the right number of electrons. The only subtle piece is, well, I have to have some correction for the correlations, and it turns out that I can write it down in a particularly simple form in terms of just this density and not some more complicated kind of thing. Any questions? So far. Okay. That's density functional theory in a nutshell. Now, that's all nice, but if you want to do some calculations, of course there should be a big question, which is, okay, fine, well, what's this magic function that I need to use so I can get all the results that I had shown you earlier? Well, the problem is, of course, there's no free lunch. The problem is, we know that that function exists, but it's a proof. It's an existence proof. It's not a proof by construction. So we don't have a good formula for this that we can then stick in the computer and start doing these minimizations. There is, however, a very good approximation called the local density approximation. And most of the results I had shown you were calculated within this. This is known as the LDA. And it says that that term can be written down, depends on the density, be written down in the following simple picture, which is also, I think, pretty intuitive. So, if you remember, I've got my little electron cloud over here. I'll redraw it. So I've got my nuclei. I've got my little electron cloud. Excuse me for that squeakiness. And then, what I do is I take my electron cloud and I divide it into a bunch of little chunks. A bunch of little volume elements, and I look at the density at each element, n of r. Then I take that little chunk of electrons out of that molecular environment, and I insert it into a system where the electron density is constant and happens to have exactly the same constant density equal to the density where that box came from. So it's the same box that I had before, just now it's in a different environment. It's in a homogeneous, uniform environment. And what we want to say is that, well, the energy of this box in this uniform environment, as an approximation, we're going to take it as that being the same as the energy it had in that other environment. That's the basic approximation. If the electron density isn't varying too rapidly, then we might hope that this is a good approximation and that the thing is going to work. The other reason why we like the homogeneous system is because it is homogeneous, it's simple, and we have various ways of computing the energy of this electron gas. And so then we can look at what these other terms are giving us, right? And seeing how much energy would be in that missing term. And we can calculate that energy per unit volume, which we call F of R. And then I can take the energy of that little box, which would be F xc, evaluated at that density, which is where this uniform piece is. That's the energy per unit volume associated with that one remaining piece in the uniform case. And then multiply by the volume to give me the energy of that little piece, or my model for it. And I add them up. And that's my total missing energy piece. And the beauty of this, as you saw already in the slides, is it's good, within a few percent accuracy. We can calculate pretty much any materials property we want for any material, just using the description I've given you here on that. Any questions on that description? Or overall? Definitely let me know if anything's not quite clear, because that's the theory, basically, what's on these 3 panels that we're going to be working with for the rest of the module. Right? Our job is going to be calculating this minimum. Yes, Chris?
Do you know what the small parameter is that is responsible for that being small enough?
For this being small enough?
Is there?
I'm not sure there's really a...
If we had muons instead of electrons, for example.
Say what?
If we had muons instead of electrons,
would this work better?
Or worse?
I think my guess would be, this is just total guessing off the top of my head, probably worse. We probably like the fact that the electrons are tend to spread out more with their lighter mass. That would just be my first guess on that. It's a fair question. Now let me think. So last semester we actually gave an estimate of how accurate this should be, based on, and this gets into a longer story I don't want to get too far into. You can rewrite this total energy, in an exact adiabatic coupling form in terms of some average exchange correlation hole, which has to satisfy the fact that it contains a single electron and integrate up to a single electron, and by basically making but it has some unknown shape. And if you make a maximum entropy estimate for that shape, you can get an idea of how accurate the theory should be. It actually gives you a pretty good estimate corresponding with what we actually see. So then the question would come down to, well, how do I think that estimate would change as I change the mass on the particles?
I didn't really mean to ask about muons. I just meant, how can you recognize a situation where it's likely to be worse than usual?
Oh, for like an actual particular material system? Well, the lore is, and it does seem to hold fairly well, is that how do I put it? The more localized your system is, the steeper the electron density changes are, and it actually does tend to hold pretty well. That atoms are the worst possible case, their energies. Surfaces then are kind of intermediate, and then solids do a bit better. So that's the one guideline for that. Yes.
I know muons would have to be worse because muonic hydrogen fuses. If you give it like if you have muon like deuterium and tritium, that fusions. So clearly it's pulled together close enough that everything else is broken down.
All right, fair enough. It probably goes with the higher mass. Yes. Okay. All right. Yes.
So, related question is there something where this completely breaks down?
Is there something where it completely breaks down? Depends what you mean by breakdown, right? So, people's favorite example for the breakdown of density functional theory would be, say, it doesn't predict superconductivity. Either traditional, but that's not too shocking because, we're working within the Born-Oppenheimer approximation, or like high temperature superconductivity. But the thing to keep in mind is that even though it does not capture those more exotic phases of the electronic system, it still describes the materials fairly well in terms of their lattice constants and the distribution of the electron density within them and so forth. So it's quite common actually to carry out a higher level calculation by first doing a density functional theory calculation to get a basic idea of the locations of the atoms and what the overall structure of the material is, and some idea of a good single particle basis in which then to do your higher level theory. But it's just not designed to get those subtle energy scales that that's why you completely miss something like superconductivity. But the energy scales associated with it relative to the accuracy we expect from this is pretty small. We expect, so for instance, I'm giving you a rough estimate of about 5% accuracy. Well, if you think a typical bond energy might be about 2 electron volts, right? That might be some kind of bonding energy. So what I'm saying is 5% of 2 volts, your uncertainty then is typically in calculating cohesive energies and things, energy scales of about 0.1 electron volts. So anything on like a superconducting energy scale is much, much smaller, is significantly smaller than that. You're just not going to pick it up. Now people do, but really getting kind of far afield here. You can build up different kinds of density functional theories where your underlying description isn't just a set of single particle orbitals, but a set of paired, a 2-coordinate set of functions, and to try to capture correlations at a higher level in those types of terms. All right, good. Good discussion. Other questions? All right. So what are we going to do next? Now we're going to try to, keep an eye on the time, begin a computational attack on this problem. Right. You've got the theory. We now want to go ahead and try to compute with it. The ultimate goal here, of course, is going to be for you guys to be able to compute with it so that you can, if you will, live the dream of Empedocles. My kind of personal view is, well, there's lots of density functional theory software that's available out there for people to use, and you should run it, and it's good stuff. But if you haven't ever just once built your own code and done it, at least a moderately well-functioning code, you aren't really living the dream of pure human intellect, basic laws of nature, predicting your material experience. So anyway, it's a little pitch for giving the course a whirl here. Okay, so computational attack. For any problem, there's a series of things you should go through. The first step always is to make as many analytic simplifications as possible. It's generally a bad idea to just try to throw something on the computer first. We want to use our brains here. Yes?
Just to, the other side of it is some methods, such as Monte Carlo methods, sometimes you're better off attacking it at a more direct level than you can make analytic transformations which make things singular in such a way that it looks nice on paper, but the methods are less efficient.
So let's say smart analytics. Or the right analytic simplification. But fair enough, right? But that's what makes this all kind of fun. Sure, fair point. You can transform things. They look. Yeah. Point. All right. So some analytic simplifications we can make. So the first one, and this may seem trivial, but from a practical point of view, it's often critically important. And that's something I always like to give a little speech on because it cost me something like 2 weeks of all-nighters of my life when I was back in graduate school because someone did not do this. And that is to choose an appropriate system of units. Basically, I'm recommending you carry out a dimensional analysis of the problem. So what happened in my experience was the code I had inherited as a graduate student was in a system of units where the unit of energy was the electron volt and the unit of distance was the angstrom. And as a consequence, this combination of constants, which seems to be appearing everywhere, had some value like 14.257. Right? And that value appeared in various places in this code in various subroutines. And in one of them, someone typed instead of like 14.257, 14.275. And this was messed up enough that it was breaking some of the high-strung algorithms that I was developing, and I couldn't find that bug to save the life. Because I read through all the code. Of course, you're looking at the code for the bug, right? I double-checked all the formulas were right, what the heck was going on, and that thing was in some data declaration at the top of the function, and even it looked right because he had just transposed like the third and fourth digit or something like that. I don't know if it was through editing or I like to think it wasn't malice, but I'll tell you. I was suspecting all kinds of things by that second week being up all night. All right. So anyway, a good system of units. So here, what shall we choose for our system of units? Well, you'll notice, of course, right? You can always set 3 independent quantities. And we're very lucky here. It turns out there's only 2 independent combinations that keep showing up, right? There's Coulomb constant E squared. We've got that everywhere, right? And it's all fun and you can laugh now. But I wasn't laughing for those couple of weeks. And I really like to emphasize people should do that. And h bar squared over n. So I like to set those both to have numerical values of 1, kc e squared, and h bar squared over n. Notice I don't set the mass electron and Planck's constant all independently to 1 because I'd like to keep as much flexibility and freedom in the end as possible. I only need to set 2, and then I'll have some choice in what the third unit might be. Let's see, kc e squared clearly has dimensions of energy times length, right? Because I divide by length, I get a potential energy. This guy, I want to make that 1. E is my unit of energy, L is my unit of length. This guy here, I multiply by a del squared to get an energy, so that's clearly energy times distance squared, right? It's one of those units. Then I can solve for my energy unit, my length unit by dividing these two. So 1 unit length must be this over that, right? H bar squared over me kc e squared, which turns out to be the well-known Bohr, and that has a value of about 0.5291 angstroms. So we'll just remember when numbers come out of our code, that's the unit of distance. The energy unit I get by dividing this one by my length, so 1 energy unit then, is going to be kc e squared over this thing, so kc e squared me over h bar squared, and that turns out to be what is known as the Hartree, which is 27.21 electron volts. And now, having set those to 1, of course I can eliminate all these guys. Yeah. I think I've got them all. And I'm still free to choose something else. You have different choices. If you want, we don't usually do this, if you make the mass of the electron 1, that's nice, and then the speed of light will be the inverse fine structure constant, right? We typically like to make the mass of the nucleon equal to 1. convenient when we're starting to deal with masses. And then you end up with a system of units where the unit of time, one time unit, is 10.18 femtoseconds. And for some applications, that's a better way to go. So it depends what you're doing. But you will like to preserve that freedom, because you really don't want any fundamental constants in any system of units if you can avoid it in your code other than Unity. All right, so that's the first simplification to make. The second one, and where am I going to go with this guy here? So I'll take this one. In this case, if you start to look at the structure of the various energy terms, computationally, one of these terms turns out to be much bigger pain in the neck than the others. Right? You'll notice all of them look pretty easy, and that they are at worst a single integral, right? Except for this mean field Hartree energy. This involves a double integral over space. And if I try to implement that directly, I'm going to be summing over independently r and r prime, which is some 6-dimensional sum. That's going to start to get expensive. So we'd like to eliminate that double integral, just as a computational. So, which I guess goes to Eric's comment, right? We want to make simplifications which you anticipate, though sometimes you're definitely wrong. That's how life is, that you anticipate to make the computation simpler. Well, one way I can get rid of that double integral is to say, okay, I'm going to write the Hartree energy this way instead. 1/2 integral n of r times phi of r d cubed r, where phi of r then is the remaining piece of that double integral. It's an integral n at r prime d cubed r prime over r minus r prime. Something like that. Now, of course, really all I've done is rewrite this, and I've just shuffled the problem under the rug, because now I have to do a 3-dimensional integral for every single point in space. I haven't really improved my situation that much yet. And this is the old problem, of course, of action at a distance, right? I'm coupling points at different locations in space. One way we can get around that action at a distance thing, of course, is to take the field seriously and look at the field equation, because that then just couples neighboring points in space. And the corresponding field equation here would just be, so I guess I don't put this here. Poisson's equation, right? Doing that integral there is equivalent to solving Poisson's equation, where this is playing the role of the density, plus the appropriate boundary conditions. When you specify those boundary conditions in this equation, you'll get the same result. And so that's the tack we're going to take in this course. We're going to be actually solving Poisson's equation. And I'm going to be anticipating a little bit, but just to let you guys know, of course, the boundary conditions that we're going to work in, because ultimately we're going to be interested in doing solids, and we're solid state physicists, so we're just more familiar with these, will be periodic boundary conditions. And the basic approach then is, if we want to study an isolated molecule, we're just going to put it in a big box with a lot of vacuum around it, and just hope then that the images aren't interacting with each other very much, if you want to do a molecule. There are, smarter things you can do, but, for this course, we're going to settle for that kind of approach. Okay, any questions? So those are the two basic steps in a general computational attack that I wanted to follow, or to recommend to you. And now, because I don't need this guy here so much anymore, what we're going to do is try to focus on solving Poisson's equation. And the goal here is basically going to be, well, this is a nice little bite-sized piece of the overall computational problem. as we solve this little equation first, which is what we'll do in this lecture and next lecture, we will actually be building up all of the computational infrastructure that we're going to need to take on this much larger problem. So it gives us a nice foil to think in terms of a smaller target problem. And it's definitely one of the components we're going to need for the overall frame. Okay, so solving Poisson's equation, if we were handed this thing, we'd go down our list of, computational attack. And we've already done step 1, if you will, which is simplification. We're looking at Poisson's equation here. Looking at Poisson's equation, we've already done the dimensional analysis. There are no residual dimensions there, plus the periodic boundary. It's about as simple as we're going to get it. The next thing we have to do before you take on any computational attack, well, let me ask you guys. All right. So now we're going to try to jump in and solve that on a computer. What's the first thing that we're going to try to do next? And by the way, this you have to go through for any computational attack on any physics problem. Hopefully you've massaged it in the right direction. Then what anybody say? I just gave you that equation. And let's not make any big overall point, philosophical point about it yet. Just what would you do next?
Choose a basis or discrete space. No?
Right. What you have to, you are doing, or giving 2 examples of, you have to choose your computational representation. Exactly. Right. If you're going to put this thing on the computer, you're going to have to figure out how to represent the physical state of your system. In this case, I've got these continuous fields to represent. And Eric gave exactly the 2 different ways we typically might go about this. You could, I forget how we put it, right? You could expand it in a basis. So for instance, we could take the density n of r and say it's going to be equal to a sum over some finite number of coefficients, expansion coefficients, which I'll call n hat alpha, times a set of basis functions, which I'll call b alpha of r. And similarly, we are going to probably want to expand our potential on a basis. That's one choice, a basis expansion. The other common choice, what would you say? The other choice was, what was the other one you gave? Basis or?
Discretized space.
Yeah, discretized space. In other words, represent the function by sample values of the function at different points in space. So I could have this basis set expansion, and then I could gather, this finite set of basis expansion coefficients that I'm going to use. I could gather them into some kind of a vector. I might call it n vector hat, some vector of expansion coefficients. This is some vector of expansion coefficients for phi. Or what I could do is I could look at the density evaluated at some discrete finite set of points in space. Right? And those values on that discrete set of points, I could again gather into some kind of computational array or something. Similarly, I could look at sample values of phi at different points, phi p, in space, and I could gather then this collection of coefficients into some kind of a vector, and this into some kind of a vector, phi vector, without the hats. Now, which choice you want to make there, depends to a large extent on the problem you're trying to solve. I would say most often, in one dimension, sample values are definitely the way to go. It's very easy to lay down a very fine grid, 10,000 sample points, and do your computation with some finite differencing, and very quickly you'll get pretty good results. As you go into higher dimensions, 2 dimensions and 3 dimensions, well, that 10,000 to the various powers of the number of dimensions starts to add up pretty quickly. So if your functions are relatively smooth, then as you get to higher and higher dimensions, oftentimes you'd rather go for a basis set expansion. And 3 dimensions is really right on the borderline. So we could kind of go either way. But it's getting close enough that I prefer to do it in a basis. So we're going to work with a basis set expansion. So this is going to be how I'm primarily going to deal with Poisson's equation. So I've got my representation there. The next thing I'm going to do, and you can kind of start to anticipate what's going to happen, is I'm going to insert these expansions into my underlying equation, right? In order to then develop some set of relations or equations among the data, in this case, my expansion coefficient vectors, that represent the physical state of my system, that I'm going to try to solve the resulting set of equations somehow using some kind of a computational method. That's the overall approach now. So we're getting close to actually implementing this thing down into software. But before we dive right on in, I did want to speak a little bit to this expressive software concept, because it's going to affect how exactly we begin to try to express the relationships among the various coefficients that we're going to try to solve. So, and again, this expressive software idea is really more of like a philosophy, a step-by-step method. But I think you'll find it very useful. So here's the basic idea. Over the years, I've observed in many painful moments of debugging that the primary source of bugs in physics software come from translation errors. What I mean by this is, you're doing your derivation, you're trying out different theories, you come down to different equations, you've got your equation, and then it's time to put that thing into the computer. But the problem is that your natural language, in terms of what you're thinking, is not the computer language. So when you type your equation or whatever it is into the computer, you have to translate in your head as you're going from your page to what's in the computer. And inevitably, the hardest to find bugs usually have something to do with an error in that translation, such as the calling interface to the function that you wrote isn't exactly what you thought it was, or when you type the thing down, you put like a parentheses in the wrong spot, those kinds of things. And then when you have some bug, you're trying to figure out where you typed the wrong thing, you have another translation problem. You're reading lines of code. Oh yeah, another typical one is you define some temporary variable, right, and then you kind of reuse it later, but you weren't supposed to, all that kind of stuff. Is all because the language in which you are writing the code doesn't fit your natural language. And then the debugging, like I said, has a similar problem. It's translation again. You're reading these different lines of code, and you're sitting there thinking, okay, what does that do, and what does that correspond to here on my page? And that's where I think the hardest and biggest waste of time comes up in trying a computational attack on a problem. And it's funny, but in a way, the computer scientists are working against you. I'm not like a big conspiracy theorist or anything, though maybe I'm starting to sound like one. But they are, because if you think about it, computer scientists are designing these computer languages. But they design them sort of in the way, if you think about it quite naturally, the way they think. And to solve the kinds of problems that interest them, which aren't necessarily the kinds of problems that interest us. So something like C++ and its various structures and so forth might be very well designed for designing a Windows manager or something like that, right? It's not designed for solving Poisson's equation. Or similarly, Java is great for web apps, sure, but it's not necessarily best for writing physics, so you end up doing this whole translation back and forth. So what the expressive software philosophy is basically, well, wouldn't it be nice if we could write the code in our natural language? If we could accomplish that, then coding would be the following. You would derive in your natural language whatever piece of physics it is that you want to do. You might make a mistake in there, but that's fine. That's where we want to be making our mistakes, right? We want to be doing physics, not translation, and not computer programming. But anyway, so you do your derivation. You get to your line, that your expression that you think is what you want to implement. Then you go to write your code. And wouldn't it be great if writing your code was simply looking at your paper and typing in exactly what you see on your paper? If you could do that, that would radically reduce the translation that's going back and forth. So first, it's harder to make a bug. And secondly, when you're debugging, you'll be able to just read your code rather than having to translate what the code is doing is trying to compare it against what you're doing. It's a little bit like you guys probably have had this experience. How many of you have written papers or lab reports in like LaTeX? How many? All right. You know how after a while, like if you're doing a derivation in LaTeX, pretty soon, like your natural language kind of gets retuned into LaTeX. Like you can do your derivation in LaTeX. You're not like writing it down and then translating it. You're actually thinking in LaTeX, and that's nice, and that's much easier. You can copy lines, whatever. You guys have had that experience. So that's the kind of experience I'd like to have. The problem is that the computer languages are a little bit different from our natural physics language. Like you can't really, there's no del squared on the keyboard, for instance, right? But if we tune our natural language just a little bit slightly to get it just a little bit closer to the computer languages, and I'll show you how to do this, then you'll begin to be able to think in an algebraic language, right, which then can be transcribed directly into software. And once we achieve that goal, and this is pretty much how the course is going to be structured, then when it comes time to implement density functional theory, I'm just going to basically write down these various terms in our new natural language and derive them, right? And then you're just going to type them in the computer, and the thing is going to work. At least that's the plan for now. So I think we're almost out of time.
5 minutes.
5 minutes to go. All right, we'll try to squeeze out the last 5 minutes.
You're allowed to give people a break.
Well, I'll go for 5 minutes. That's fine. All right, so let's start this off, right? We're going to solve possibilities. Can I do this? No. I'll tell you what. We will give it a break. Because I want this to go coherent. So the point won't be punctuated properly. All right. We'll see you Friday. Friday we'll apply this expressive software concept and see if I can sort of meet the goal I've laid down of being able to teach you a slightly tuned natural language that we can then type literally into our software. All right. That's it.